Thank you, Guntao, for giving this opportunity and also for the nice introduction. I want to talk about polynomial chi-boundedness. So let me tell you what chi-boundedness is. So chi-boundedness is the relationship between two graph invariants. And the first graph invariant is the chromatic number, and we use chi for denoting that. So that's why it's called chi-boundedness. So the chromatic number, you want to color the vertices so that every edge, the endpoints are colored differently. And the challenge is to use the smallest number of colors. And historically, it has been one of the driving forces for graph theory with the four-color theorem. And here I put a small picture of Francis Guthrie asking the problem in 1852. And so the four-color problem lay around for quite a bit. And we already saw this today. Tate had reformulated that and a lot of people thought about it. But Brooks gave a theorem about the chromatic number of an abstract graph in terms of its highest vertex degree. And then it was taken up by Dirac, Galai, and from then on, the chromatic number has been the subject of a lot of research. So one can argue that it is probably one of the most famous graph invariants. And a big question is what causes large chromatic number? So we understand graphs with chromatic number 1. We understand graphs with chromatic number 2, well, pretty well. But more than that, we don't clearly understand what causes a graph to have large chromatic number. And this can be formulated in many different ways. And in terms of substructure, you can talk about different notions of containment. You can talk about minors, you can talk about subgraphs, you can talk about induced subgraphs, you can talk about immersion or whatever notion of containment. And probably the single most famous problem in graph theory is called the Hartwig's conjecture, relates the chromatic number and the size of a largest clique minor. I will not go into this because that's not the subject today, but Hartwig's conjecture also can be thought of as a chi-boundedness thing because it relates the chromatic number. And the second invariant in the chi-boundedness relationship is the clique number. The clique number, what is a clique? A clique in a graph is just a set of vertices. Any two, there is an edge between them. So it's the subgraph that is complete. And the word comes from social connotation. Clique is a group of people who have similar interests. And the largest size of such a set is called the clique number, and it's denoted omega. And what is the relationship between these two invariants? That's the story of chi-boundedness between chi and omega. Well, right away, omega is a lower bound for chi, because if you have a clique of size k, you need at least k colors, even to color just those vertices, let alone the whole graph. And if the clique number is 1, then chromatic number is 1. That's easy. But even when the clique number is 2, which just means that there are no triangles, triangle-free graphs, what is the chromatic number? This has been investigated pretty heavily. And there are a lot of constructions which tell you that there are triangle-free graphs with arbitrarily large chromatic number. So just by the knowledge of the fact that omega is 2, there is no way you can say what the chromatic number is. And in fact, this actually led Ardèche to prove, using his probabilistic argument, a famous theorem, which says that you can have graphs of arbitrary large girth and arbitrary large chromatic number, not just triangle free. You can just free of all small cycles. There are graphs. And that will be used throughout the talk. That's such a fundamental and basic theorem that we'll use it all the time. So the story of chi-boundedness is the relationship between chromatic number and the clique number. As we saw in the context of minors, that is manifested in the Hartwig's conjecture. But we are mostly interested in induced subgraphs, and that's where the relationship between chi and omega kind of nicely comes out. So what is an induced subgraph? You have a graph and you can only delete vertices. You cannot delete edges. And whatever you get by deleting vertices is called an induced subgraph. Of course, we are talking only up to isomorphism. So we don't care about the labels. So here are some early results. Wiesing in 1965 famously proved his theorem on edge coloring, which can be rephrased as, for line graphs, the chromatic number is at most the clique number plus 1. And Shinsei in 1974 said that if your graph is P4 free, P4 means the path graph on 4 vertices. Already we saw P4 playing an important role in Professor Keisted's talk. So P4 free, then he proved that the chromatic number and the clique number coincide. This is a very, very nice paper, 2-page paper. Everybody should read this. And the reason is, I'll let you know the reason in a second, but let me just give all the 4 results. Wagon in a 1-page paper proved that if you are 2K2 free, 2K2 is just the graph on 4 vertices with just 2 edges, then you get a quadratic bound. And Gyarfas in 1987 said, how about excluding any path on T vertices, a path on T vertices? He introduced what is now known as the Gyarfas path argument, very, very influential, and which gave him this bound. But unfortunately, this bound is exponential. So we ideally would like to reverse the roles of omega and t in this bound, but nobody has been able to do that. So the Shinsei result is very nice, and it's different from the bottom 2, because what he does is he gives a way to construct all P4 free graphs. P4 free graphs have become very famous. They're called co-graphs now, short for complement reducible graphs. And he gave a construction, very simple construction. You just have to take disjoint union or disjoint union plus put all possible edges, also called join, of 2 previously constructed P4 free graphs. And you get a new P4 free graph. And if you start with just K1, 1 vertex graph, you can get all P4 free graphs this way. So very, very simple construction, recursive construction of P4 free graphs. So you can test any theorem on P4 free graphs by using this theorem. And they have very nice algorithmic properties, very nice structural properties, and a lot of things. So they have been very inspirational, this class of graphs. So these are some of the results where you exclude something, you get a bound, a connection between the chromatic number and the clique number. And this is one of the main lines in the theory of high-boundedness. Wiesing's theorem, it says G is a line graph, but a line graph, Beinecke characterized in 1968-69 that line graphs have exactly 9 forbidden induced subgraphs. So you can restate this theorem in terms of saying that if your graph has none of these 9 little graphs as induced subgraphs, then you get this bound. Chi is at most omega plus 1. In fact, as we are going to see later, Keisted proved a generalization of this theorem. You don't need to exclude all the 9 to get this bound. You can just exclude 2 of them. So, but meanwhile, there was another line of development based on the relationship between chi and omega. Burge was interested in this, and he said a graph is perfect if these 2 numbers are equal for all induced subgraphs. Why did he do all induced subgraphs? If not, it's not very interesting. You won't get anything if you don't require it for all induced subgraphs. It's just not a robust notion. So, but this doing it for all induced subgraphs turned out to be a major event, because many fundamental graph classes are perfect, and comparability graphs, which come from partially ordered sets, interval graphs, chordal graphs that I just made, chordal graphs, and many are fundamentally perfect. And Loas, 1972, famously proved that the complement of a perfect graph is perfect. And this result is also mentioned in the Abel Prize citation for Loas. So this was one of his earliest results. And Rochel, Lowash, and Shriver proved that they have fantastic algorithmic properties. So what is happening is something deep is happening. If you require that these two parameters are equal for all induced subgraphs, suddenly these graphs tend to behave much more nicely than just general graphs. And the final Fulkerson Prize winning paper in this series of developments was the determination of the forbidden induced subgraphs for perfect graphs. And it's very simple, just the odd cycles and their complements. Just odd cycles and their complements. And cycles start at 5. Triangle is perfect, right? K3 is perfect. Okay, so from this line of development, Gyarfas said, if your graph is not perfect, maybe still we want to quantify it using perfection or this relationship between chi and omega. And that's where he defined this notion. A hereditary class, which means a class which is closed in an induced subgraph, is said to be chi-bounded if there is some function whatsoever, such that the chromatic number of every graph is at most f of the clique number. And this turns out to be a good notion. And he posed 4 problems for a general hereditary class of graphs. Suppose somebody gives you a hereditary class of graphs. Is it chi-bounded? And is there a polynomial function? So here, f is just any function, but for approximation algorithms and a lot of things, we are interested in a polynomial chi-bounding function, if there is one. And of course, we would like the polynomial to have degree 1. Is it linear? And finally, if you understand enough about a class, what is the optimal chi-bounding function for a class? So these are 4 questions that you can ask immediately for any hereditary class of graphs. And let me begin with some 3 theorems on chi-boundedness, which were conjectures of Gyarfas in his original paper, which were proved recently by the Princeton School of Graph Theorists around Seymour. So a hole in a graph is an induced cycle of length at least 4. So triangles don't count. So they proved that the class of odd hole free graphs is chi-bounded. And for any t, if you exclude holes starting at that length, t plus 1, t plus 2, all the holes starting at that length, then it's chi-bounded. And finally, combining the 2, they proved that if you just starting at t, you just need to exclude only the odd holes, then it's chi-bounded. And in fact, there is actually generalization of this result as well due to Scott and Seymour. And all these 3 prove chi-boundedness, but they are very, very far from being a polynomial. So an open problem in this area is to determine whether these theorems can be modified to give a polynomial chi-boundedness result. And the reason for looking for that is actually a conjecture of Esperet, which I'll tell you in a minute. But this connection between the chromatic number and the clique number actually implies a conjecture of Erdős-Heinen, which states that whenever you exclude any graph as an induced subgraph, the size of the largest clique or stable set just becomes very big, polynomial. Polynomial meaning n to the c. And it works for any h. That's the conjecture. So for any h, if you exclude it, the class you get has this property of having a large stable set or a clique, which is unlike the usual general class of graphs where you can have only logarithmic size stable set or clique. So this is probably a very, very important conjecture in induced subgraphs, because it's saying that it works for every graph h. So that's the value of this conjecture. This is very hard. Recently, Paul Seymour and Maria and Sophie Sperkel and Alex Scott proved this for C5, which was a big news. It was in the Quanta magazine as well. So this has been proved for H equal to C5, the 5-vertex cycle. But it's still open for the 5-vertex path. So, okay, the main conjecture that is interesting from the talk's perspective today is that Esprit is kind of leaning towards saying that whenever a graph class is chi-bounded, you can actually find a polynomial that works. Find a polynomial that works. This is in some sense like the P versus NP problem. P versus NP in computer science says that whenever you can find a polynomial time non-deterministic Turing machine to do a job, you can actually find a deterministic Turing machine to do a job in polynomial time. Something, I mean, very rough comparison, but I think that's what it's saying. Whenever you have a chi-bounded class, if there is a chi-bounding function, there is always a polynomial chi-bounding function. So that's what the conjecture is. We have very, very little evidence either way for this conjecture. And so the Gyarfas-Sumner conjecture says that when you exclude a tree, then the class you get is chi-bounded. And why should we exclude just a tree, not any graph? Well, that's because of the address theorem. If your graph had a cycle, there's no chance it would work. It's an immediate consequence of that theorem. So this would work only for a forest. So I just put a tree, but you can replace it with a forest. But it turns out they're equivalent. If you can prove it for trees, you can prove it for forests, all forests. So this is also an important conjecture. So, okay. So there is this notion of vertex minor derived from induced subgraph. Instead of just excluding one graph as an induced subgraph, you exclude a family of graphs as an induced subgraph. What family? You take a graph, you take a vertex, you look at its neighbors, you just complement on the neighbors. And you can keep doing this. So you get a bunch of graphs. So if you exclude all these graphs as induced subgraphs, that's saying that it's free of vertex minor of the first graph that you started with. And with Kim, Ojang Kwong, and Sangil Om, we proved in 2018 that if you don't contain a cycle as a vertex minor, then you're polynomially chi-bounded. So, but after this was generalized vastly by Monami and Filipchuk, who proved that the class of graphs with clique width is an important parameter in algorithmic graph theory. It's the smallest number of labels you need to require to build your graph in a certain way. Most K is polynomially chi-bounded. This was published in Advances in Combinatorics. And the reason we were interested in vertex minor was this theorem of Gielen from 2009. He said that it should work for any graph, not just a cycle. It should work for any graph. So this is like the Erdős-Heinel conjecture. Any graph you take, exclude it as a vertex minor, then what you get is chi-bounded. And last year, it was proved, this conjecture of Gielen was proved by a student of his called James Davis. So this is now a theorem that if you exclude any graph as a vertex minor, it's chi-bounded. So that leaves us with a conjecture. So now we know that it's chi-bounded. Is it polynomially chi-bounded? So for any graph H, the class of graphs not containing H as a vertex minor is polynomially chi-bounded. Okay, so what we proved was for a cycle it works. And so I think this is a good conjecture for graduate students, especially if they're dealing with like structured graphs. Take something similar to a cycle and make the argument go through. Okay, so how do we prove chi-boundedness results? How do we prove chi-boundedness results? One notion that Huang and McDermott came up with was called divisibility. So in number theory, people have divisibility. So we do. So in graph theory, divisibility in this context means you want to take your graph and to break into pieces so that the pieces are much more well behaved. And since we are interested in chromatic number and the clique number, divisibility, there is a notion of divisibility called two divisible. A graph is two divisible if you can take the vertex set and partition into two parts, and in each part, the clique number goes down by 1. So suppose the clique number was 10 when you started with. When you break into two parts, the clique number has to be at most 9 in each part. This is actually very related to the clique chromatic number that was the talk given today about the Prague dimension. So that's two divisible, and it has to work for all induced subgraphs, not just for the graph. And it's easy to see that if your graph is two divisible, then you get chi-boundedness. And with Maria Chudnovsky, we proved that if you exclude a path on 5 vertices and a cycle on 5 vertices, you get two divisibility. You have this nice property. So you get a nice chi-bounding function, which is 2 to the omega. I mean, it's nice, but still not a polynomial. So whether these graphs have a polynomial chi-bounding function is still one of the basic open problems in this area, because P5, C5 looks like we're excluding a lot, but we don't know their structure. We don't know their optimal chi-bounding function. Algorithmically, some things are known, but the chi-bounding function, does it have a quadratic chi-bounding function? We still don't know. And with Maria, we also proved that a bull is a 5-vertex graph, which just comes from a triangle with 2 edges hanging off. And it's nice because the bull is isomorphic to its complement. And we proved these 2 theorems as well, that these graphs are perfectly divisible. Perfect divisibility is more interesting than two divisibility, because what is perfectly divisible? You can partition your vertex set into 2 parts, such that in the first part, the clique number has gone down. The second part is actually perfect. Second part is actually perfect. So, and if you work out by induction, you will get a quadratic chi-bounding function for perfectly divisible graphs. So perfect divisibility is a very, very nice tool to prove that certain classes are quadratically chi-bounded. And here is a conjecture that actually these 2 graph classes are the same. Odd hole free graphs are 2 divisible. That's a nice conjecture, structural conjecture. But as far as polynomial chi-boundedness is concerned, one line of development has been, oh, you exclude this, this, and this. Can you get polynomial chi-bounding functions? Okay, and a lot of results are known today. Of course, a lot of things are also open, but there is a recent very nice survey in the journal Graphs and Combinatorics by Schermer and Renderer on a lot of these things. And especially if you're excluding 2 graphs or 3 graphs, a lot of results are known. I just put 2 things from the speakers in this conference. So Kiersted proved that if you exclude the claw and K5 minus an edge, then the chromatic number is at most the clique number plus 1. This is a generalization of the Wiesing theorem that we saw, because in Wiesing, you have to exclude 9 things in order to be a line graph, and these are 2 of the 9 things. Okay, this is a generalization of that theorem. And with Katie Cameron, Shinmei Huang, and Irana Panay, we proved that if you exclude certain combinations of paths and cycles, you get this chi-bounding function. And the reason for interest in this was we actually obtained a structure theorem. We obtained a structure. So there are several ways to get chi-boundedness results. You actually prove a structure theorem, which will be more useful from an algorithmic point of view, and then use that to get your bounds. Or if you're using divisibility, you're kind of bypassing the structure theorem bit. You're not understanding the whole graph. You're just saying one part of the graph is perfect. I don't care about it anymore because I know it can be colored with omega colors. So there are several sides to the chi-boundedness result. And as I mentioned, and there are several nice open problems here with different combinations of paths. And if G is P5 and C5 free, is it quadratically chi-bounded? This is still not known. This would be very, very interesting because of its connection to the Erdős-Heinel conjecture. Okay, and early this year we wrote a paper where we were interested in excluding a fork. A fork is the graph K13 with an edge subdivided. You take K13, the complete bipart, the cloth, right? Complete bipartite graph with one vertex on one side, 3 on the other side, and you subdivide one of the edges. That's called a fork or a chair. And we wanted, so I conjectured that if the class of fork-free graphs are perfectly divisible, that conjecture is still open. It's a nice conjecture, I think. So the class of fork-free graphs is perfectly divisible. It's still open, and that would give a quadratic chi-bounding function for fork-free graphs. And what we did was we analyzed fork H-free for certain combinations of H for 6 graphs, and we proved that they are perfectly divisible or claw-free, and we get a quadratic chi-bounding function. But very few months after that, there was a nice breakthrough that Liu, Schroeder, Wang, and Yu actually proved that the class of fork-free graphs is quadratically chi-bounded. Quadratically chi-bounded. So, and they have this quadratic chi-bounding function, 7.5 x squared. And in fact, they do more than that for a T-broom free. What is a T-broom? You take K1T and subdivide one of the edges. And this is a very, very nice paper. So this is a very recent one. And they proved this chi-bounding function. And tomorrow, Wang will talk about this in his talk tomorrow about these two results. That's the last talk of the conference tomorrow. And inspired by this, Scott, Seymour, and Sperkel proved this result that related to the Giaffa-Sumner. So if you exclude a forest, then it's polynomially chi-bounded when the forest has a very specific structure. They proved two theorems. One, when the forest, each component of the forest is a star. And the other one is when there are only 2 vertices of degree greater than 1. That's what is called a double star. So this is also a very nice recent development on this end. And the another line of development has been on geometric intersection graphs. I don't know much about this area, but it's a very, very active area where a lot of people work. And the class of circle graphs, you take a circle and you take chords, and if they intersect, you put an edge. And this class was known to be chi-bounded, but only recently they proved a quadratic chi-bounding function for this class, 7 omega squared. And in fact, a very recent paper, not even a month old, I think, they improved the results there to what they call grounded L graphs. They showed it to be polynomially chi-bounded. And this is a paper where people can look for a survey on polynomial chi-boundedness for geometric intersection graphs. So there are a couple of lines of development here. You exclude certain things, you get chi-boundedness results. In that, there are 2 flavors. You either exclude a finite set or you exclude an infinite set, like set of holes. And the other one is the geometric intersection graphs. And so let me tell you some interesting open problems in this area. The first one that I already mentioned, if you exclude P phi and C phi, then can you get a quadratic chi-bounding function? I think this is a fundamental question, and it really tests whether we understand excluding small graphs as induced subgraphs. And Scott and Seymour proved that if you're odd hole free, then they proved this chi-bounding function, which is doubly exponential. Can this be improved to a polynomial chi-bounding function? And I conjecture that there is a nice relationship between the chromatic number, the clique number, and the length of a longest hole in a graph. Chi is less than or equal to omega to the L minus 3, where L is the smallest length. Well, you don't have a hole. Okay. So And what about graphs whose complement don't have small cycles? They are known to be quadratically chi-bounded. Can you improve the quadratic chi-bounding function? And how about graphs in which you don't have big holes and anti-holes? So by big, I mean at most nothing of size 6. And the sixth problem is, this is a very, very tractable problem, I think. And if you exclude P6 and its complement, is it polynomially chi-bounded? And how about excluding a path and the complement of a 5-vertex path? The complement of a 5-vertex path is called a house. It's a nice little graph, and this polynomially chi-boundedness would mean something. And another thing people think about is even hole free graphs, graphs in which there are no holes of even length, the counterpart of odd hole free graphs. And these are much more well understood than odd hole free graphs. And the reason is even hole free, we start at 4. So C4 free, they don't have 4 cycles as induced cycles. So they are known to be chi-bounded by 2 omega, but can you make it better than 2 times omega? And in my last minute, I want to mention this important conjecture of Thomas and Espray, which says, he says that the behavior of a hereditary graph class, as far as chi-boundedness is concerned, is governed by the triangle-free members. If the triangle-free members have bounded chromatic number, then that immediately tells that the whole class is chi-bounded. This is also very, very strong conjecture. And my last question is, you could take polynomial chi-bounding functions and define graph classes. And that's exactly what Burge did. So let us call a graph Wiesing if every induced subgraph satisfies chi is at most omega plus 1. And it would be a good idea to understand what graphs are Wiesing, but it turns out that it's pretty rich. Algorithmic problems are hard, even in Wiesing graphs. So my suggestion would be to try to understand graphs in which, so that both the graph and its complement are Wiesing. So maybe there is more traction there, and maybe they kind of mimic perfect graphs in some sense. So those are my 10 problems that I wanted to share on chi-boundedness. Thank you.